The next presentation is by Esther Bekesi. She joined recently the Earth Physics and Space Sciences Institute in Chopron after a PhD in Utrecht University, and she is one of the many high potential young scientists at this institute, and she will give us here an overview of geo-energy research at EPSS, status and future advancements. Esther, floor is yours.
So welcome everyone. As Siert said, I'm a research fellow at the Institute of Earth Physics and Space Science. In this talk, I will concentrate on showing you some important competencies within EPSS that can be used for geoenergy research as well. For now, they are mostly focusing on fundamental research, but here I would like to emphasize the connection between basic research, so fundamental research, and applied research, and how these can connect. So within the Earth Science cluster of our institute, EPSS, traditional research focused on the observation of the physical field of system Earth. But in recent years, many geologists' colleagues also joined our institute, and right now this geological component, material observational component, is also very strong in our institute. So we have a wide range of both geophysical and both geological observations. And the goal within this institute is to integrate these different observations towards a better understanding of complex Earth science-related problems. So from now on, I will show you some examples for competencies that can be plugged in for geoenergy research as well. First of all, our institute basically operates the Hungarian National Seismological Network. Here you can see our, okay. I will see whether, you cannot see the laser. Anyways, here are the stations all over the country that we operate. And these observations provide very important basis for research in our institute, but it is also important to mention that it's also a public service that we use. And here it's done on a more like a larger, like a country scale, to basically monitor the seismicity of the entire region. But it's important to note that such studies can be also done on a much smaller scale, for instance, to image and monitor georeservoir. Important studies focus further on the mapping of the structure of the lithosphere. These include classical structural geological studies. For instance, this cross-section produced by one of our structural geologist colleagues, as well as, for instance, these magnetotelluric studies that can image the structure of the entire lithosphere. Research also focuses on the active deformation of the Pannonian Basin, which is done with high spatial and temporal resolution using advanced techniques such as, for instance, satellite-based radar interferometry for the observations of active ground motions in the area, combined with more stable GPS measurements. A very nice example of an integrated study is the recent large-scale project within our institute that focused on the seismotectonic analysis of the Pannonian Basin. And in the framework of this study, we worked together with some very nice colleagues from the GeoOmega company and integrated different geophysical and geological data sets and models such as stress and strain rate fields, earthquakes, as well as major structures, to produce this map, which outlines the major active structures of the area, which can be very important also if we want to target a reservoir which is located in the basement, because these critically stressed structures can easily reactivate in any kind of geoenergy applications, changing the stress field of the crust. We also do a wide range of modeling studies within our institute, starting from large scale like geodynamic models, regional scale temperature models, and we also focus on more smaller like reservoir scale to reproduce the temperature field within, for instance, a geothermal reservoir, and also do geomechanical modeling. We also largely focus on the investigation of fluid-rock interactions. We do it in with different approaches, such as numerical modeling, but also, for instance, using fluid inclusions that Marta will talk a little bit further on, which, for instance, facilitate us to directly trace geofluids in these samples. From now, I will show you some examples for geoenergy research, geoenergy-related studies that we performed in EPSS. The first example are these large-scale temperature models that we produced in collaboration with Utrecht University and the Geological Survey of the Netherlands, the TNO. These models extend from the surface until the depth of the lithosphere. So these are physics-based models that can be calibrated with numerous temperature observations, which are all gathered from wells with very efficient data assimilation techniques. And therefore, these can reconstruct the thermal field of the entire lithosphere with high precision. Of course, you can be more precise if you have the observations, especially in the top parts of these models. And recently, we developed on these models in collaboration with the TNO Utrecht to also reconstruct the thermal evolution related to the formation of the Pannonian Basin. So basically, most important applications are these models is the resource assessment aspect to provide precise temperature input to better assess geothermal potential. Moving towards more on a reservoir scale, here is an example from the Szentes geothermal area, which is one of the oldest geothermal fields in Hungary. I'm sure that János will talk about it in more details later on. This area is very interesting because there was still ongoing very intense production of thermal waters, which resulted in the reduction of groundwater levels and pore pressures in the reservoir. And what we did in here is that we looked at the active surface deformation for several years of this geothermal field and combined these surface ground motion observations with pore pressure changes within the reservoir. Here we only used very simple source models for that. Just to provide a little bit of a background about it, these processes. So when we extract or inject in the subsurface, we change the stress state of the geological environment, for instance, in terms of changing the pore pressures, which can translate to compaction, decompaction of the reservoir system that can potentially translate to surface motions. That's what we here can observe. But for instance, it can also lead to the reactivation of faults, fractures, causing induced seismicity. I will also show an example for that later on. Here in Szentes, we related these surface motions with reservoir pore pressure changes in order to better identify the deformation processes that happen in the reservoir, and therefore to get a picture about the dynamics of the reservoir system, which can later on help to assist, for instance, field management towards constructing a sustainable and safe production scenario. So here is an example of an induced seismic event. It's from Mexico. It's very far from here, from the Los Humeros geothermal field, which is a huge geothermal field providing electricity for an entire county. So I had a chance to work on this field in collaboration with Mexican colleagues. And it's a very interesting example because there's a clear connection between the increase of re-injection rates and the occurrence of these induced earthquake. So this colorful map shows the ground motions because of these earthquakes. And I'm showing this not to scare you because, for instance, in areas such as the Pannonian Basin, the relevance of these induced events is much less than compared to such an active system, but still it's very important to look into potentially critically stressed structures, especially if we want to go deeper, if we want to inject, if we want to get more energy or produce electricity from larger depths and more tough rocks. This one is just a geothermal field development study. It's in a very early stage that we did together with the HUN REN Center of Energy Research. Here we focused on an area in South Hungary. It's the region of Boy, where we combined different geological risk factors with the surface infrastructure to come up with a kind of geothermal site suitability map. Based on that, we proposed just potential geothermal doublet locations for the area, but we want to further build on this and kind of provide a better understanding on the state of the reservoir that will, of course, govern any kind of geothermal activities later in the area. So up until now, I talked about geothermal utilization where the fluid comes from the geological environment, but sometimes it's just not possible because, for instance, we don't have enough fluids or the quality of the fluids is not good enough, or anyways, there can be many unsuccessful wells where we still want to do something. A potential solution for this can be the establishment of these kinds of very deep borehole heat exchangers. As an example here, that the cold fluid goes down in the inner part and there's a central production tube where the hot fluids come up. And within the institute, we investigated different parameters, so the influence of various geological and operational parameters on the output, on the potential energy that can be taken out from these systems. So for that, we set up numerical models, and here I will just show some examples for this. This is a base case where we have a 2.5 kilometer deep borehole in a typical Pannonian Basin setting. And in the diagram in the left-hand side, you can see with the red the temperatures that can be extracted from such system on longer terms. It's still very small. Also, the output energy, if you have a look in the right side figure, in this base case scenario is around 400 kilowatts. So if we compare it to an open hole geothermal doublet, it's of course a small number, but we have to consider that these systems are much less risky, and there are cases when this can be still useful and efficient to extract geothermal energy. So moving forward, just to show you some plans we have, one of these is in the framework of the Research Grant Hungary project of SIRD. So here we plan a kind of geothermal imaging study based on passive seismic monitoring. Here we plan to combine these measurements and models that we get out from this seismic survey with other external data sets to provide a better understanding of a potential geothermal reservoir. Here, in this case, we want to test this methodology for these fractured and karstified carbonate reservoirs in the Pannonian Basin. So this will be, first of all, kind of a test, whether we can use it extensively for exploration and also to provide some new methodologies and insights for the potential application. Another very interesting potential project, it's still in a planning phase and we have to see the feasibility, is connected to a recent discovery of our geologists' colleagues who went to northeast Hungary and found very important evaporite successions, here shown with this yellowish color in the cross-section. It's very interesting because these evaporites, they are very efficient in the conduction of heat. Therefore, they can produce large temperatures in their vicinity. And here, it seems to be kind of a fortunate setting that they are basically located next to fractured and karstified carbonates with fluid content. And this is interesting because this geothermal potential is also mirrored in the presence of surface hot springs in the area. But right now we don't know that much about these structures. Our colleagues are working on geological models of the area, and based on that we are planning to set up temperature model to understand the coupling between the hydraulic and the thermal coupling between these two very interesting types of rocks. And for that, to calibrate our models, we didn't know the thermal properties of these rocks because no one ever measured them. And here it's very important because we build our kind of hypothesis on the fact that these evaporites should have high thermal conductivity to provide enough heat for these systems. So we collected some samples, my colleagues collected some samples from this area, which we sent to Lausanne University for measurements, and we recently got very interesting numbers, very high numbers for the thermal conductivity. So I hope within the next few weeks I can start working on this model because we are all very excited on the outcome. Okay, until now I talked about geothermal, but it's very, we are also actively involved in research connected to natural hydrogen, which is a very, very interesting, at least to me, new field of research because there are so many unknown, unexplored aspects of it. So there are two important proposals. I think Steed already mentioned it, one led by Gabor, this cost action, and another Horizon proposal which has been submitted just yesterday, we just submitted yesterday, if I'm not mistaken, yeah? So from now on I will just show you some preliminary or interesting studies connected to natural hydrogen that we did mostly in cooperation with Gabor, who basically introduced me or us to this new field of research. So here I will talk about these fairy circles that Gabor already mentioned. So these fairy circles, what you have to know about is that these are probably the most important surface seeps, kind of mega seeps of hydrogen. And they are very poorly understood still, and they are observed all over the globe. So basically, I see now that this version of my presentation was updated, so I wanted to show a different figure, but anyways, I can still, I think, explain this way. So, as Gabor also showed you, they are observed all over the globe. Like, here are some examples, but you can also trace many of them, for instance, in Ukraine, also in Russia, Brazil, and Australia. So, just as a bit of a repetition, what are these fairy circles? These fairy circles are subcircular depressions with a diameter of about a few tens of meters up until a few kilometers. So there's this morphological feature, but the other very important aspect that Gabor mentioned is this vegetation anomaly part. And Gabor mentioned this vegetation damage in the inner part of these fairy circles. But what's also very interesting that some of these, not all of these, but some of these are marked with this enriched vegetation zone all around, this ring of enriched vegetation around the fairy circle, which can be like another proxy, another kind of kind of a characteristics of such a ferry circle for their exploration. Another very important component here is the temporal part. So these ferry circles tend to be kind of short-lived in a geological time scale. So for instance, in Russia, these were observed to appear within a few years. And this whole seeping, so the active hydrogen emission, also is thought to live only a few hundreds of years. But actually no one constrained it so far. But what's interesting is that they seem to be active, and what we wanted to see here is to kind of better constrain this temporal component. So we used satellite radar images here for the first time to learn a little bit more about the dynamics of these structures, whether they form actively, whether these vegetation changes happen in the scale of a few years. So for that, we did a preliminary case study. Very interesting area in Brazil. I had a chance to work with this Mr. Hydrogen, Alan Prince-Hofer, in this area. Gabor already showed this figure, where an extensive soil geochemical monitoring took place, which basically confirmed the presence of hydrogen seeping. Here you see this periodic anomaly as well as large fluxes of hydrogen. And what we did here is we looked at a larger area. So on the right image, you can see already an average kind of radar backscatter images that is basically proportional to the strength of the backscattered radar signal. And if you average it, you can produce these nice maps, which are highly sensitive to vegetation. So on this map, you can see multiple ferry circles which appear as with a white outline that corresponds to this enriched vegetation zone around these ferry circles. And going further to look also into the temporal component of this, we produced these averaged maps for each year. We wanted to take like a whole yearly cycle in order to avoid any seasonal variations. And we calculated these kind of backscatter change maps. Here in the left-hand side, the green values show basically enriching or increasing vegetation, and the pink decreasing vegetation. And it was very interesting. This was just the first idea to produce these maps, whether we can see clearly any ferry circles appearing in this. And we saw many of them appearing. Here is an example in the middle where the inner part of the ferry circle is marked by increasing vegetation. Also in this cross-section on the right, you can see this high increase within a few years here, within a 5-year interval. So it was very interesting to see this temporal component, that it happens so quickly, but we still don't know how this vegetation change is connected to gas seeping. It must show that there are some kind of variation between the fluxing of these time periods, but actually measurements are only available from this Campina structure and another one, but not the rest of them. So we cannot really provide a full understanding here. What's also very interesting is that it was observed, for instance, in Russia and many other places all around the globe, that when these ferry circles appeared, a zone of dying vegetation also occurred. So possibly new ferry circles could be pinpointed with this method in terms of, here with this arrow, you can see one potentially newly forming ferry circle with the appearing vegetation damage. Oh, and going further, I will come back. I also added here an extra slide where we looked into the ground motions or the surface deformation of these structures, where we concentrated on the Campina structures to see whether there's any subsidence or uplift connected to the active steeping of gas. And we saw, in case of this structure, this Campina structure, that the inner part is actively subsiding, that might be connected to hydrogen emissions. But of course, these are just observations. For now, we cannot provide a full model, but what we see that the capacity of these synthetic aperture radar images, both for exploration and for monitoring, are basically supported by this preliminary study, which can be combined to kind of provide external constraints on the dynamics of these fairy circles and a better understanding of hydrogen seeping. So here is just another example from the group of Marta who focus on fluid inclusions. These are very important studies because they can directly trace migration pathways, for instance, for fluids, and also they can preserve the physical and chemical information from the subsurface. So here is an example about done with Raman spectroscopy for basically the tracing of different elements, in this case hydrogen, from the Chopro Mountains in this case. And the plan within these larger European initiatives is that EPS has to take active part in these fluid inclusion studies from rock samples all over the European case studies that we proposed. So it's also a very interesting component. Yes, so here is a summary. I just listed the most important competencies of EPSS for geoenergy. And yeah, we just really hope that these can really be plugged in and put in a more complex framework to collaborate with the industry, because I think there's a high potential for that, and we already have lots of collaborations, but it would be very nice to be extended and feed in to actually promote geoenergy research and successful projects. So thank you very much.
Thank you very much, Esther. Very clear presentation. Thanks. Also making absolutely evident how important the role is of collaborative research in this domain of renewable energy. And this applies both to research on the national level, also including the role of industry, but of course when we talk about a European context, it's very clear that the programs of the European Commission, which are really essential to bring this up on a fully pan-European level, play already a crucial role. And I think these integrations, both on the national level and on the European level, can create a lot of synergy. So time for one or two quick questions. The next speaker has a question. Yeah, Bernard, please.
Well, thank you for this great presentation. I do have a question on the borehole heat exchanger, actually, right?
I will go back.
You don't have to go back. It's a very simple
Okay.
question in the end, right? So when do you think a well is feasible to be refitted as a borehole heat exchanger? Means I'm talking about how deep should it be, must it be, what's the diameter, etc. Like,
Yeah.
and how many will last, finally?
Yeah. We try to kind of model this, but when I looked into it, I think if we talk about depth of 1-2 kilometers, if we want to constantly operate them, so like a constant circulation to provide constant energy, then you have to go very deep. I think at least 3 kilometers. And it's I would say it with a geothermal gradient of at least 40 degrees, so I would go deeper in the Vienna basin, but yeah, it all depends, but yeah, of course. But I think what really helps is, for instance, if you have a zone in the subsurface where you have kind of relatively quick flow in the geological environment that can help to kind of initiate or enhance the heat transfer and try to or help to with the recovery of the system. But if you want to operate them with pauses for a few hours a day or whatever, then a lot more energy, because the thermal recovery is relatively quick. And that's what I also started looking into, because many companies are interested in this now. So, yeah.
One more quick question.
Let me have a statement to that as well, please. Yeah, I love that concept, because we were looking at it in the Vienna Basin as well, because one part of geothermal energy is also reusing the old oil and gas wells, right? So they were not only for the dirty stuff, they are now done for the renewable stuff. We drilled 5,000 wells in the Vienna Basin, roughly, since the 1930s. Yeah? 1,000 are still active, or at least not liquidated. And how many do you think we think are feasible for doing that? I take that away from you, about 20. Yeah? So this number shrinks a lot. And our cutoff in the Vienna Basin, and you are placed in the Pannonian Basin with a much better geothermal gradient. But our cutoff is about 7-inch diameter in about 2,000 to 2,500 meter depth. And then there's not many wells left over to do something like that. Yeah? But yeah, the concept is cool. I like that. For OMV, as a big energy company, this was like, no. We wanted to feed a shrimp farm with that, actually, yeah? Because the temperature output is also small, as you said, 30, 40 degrees, and then you're already 3,000 meter depth. But super cool concept, I like it.
No, I just show it as an interesting potential way of, but you know, there are also these systems, for instance, this Everloop system, where you have like a very long horizontal section, which are much more effective. But of course you have to...
I hope you have a lot of money as well. Yeah.
I can model it. I'm not giving
I'm watching this next door, right?
Wonderful. I think we have to leave it here. Thanks again, Esther.
Thank you.